Hey guys, it's Miss Miklos, and today we are going to be talking about polynomial functions of a higher degree. So we're going to go ahead and get straight into this and just kind of talk about characteristics of polynomial graphs. The first one is that they are continuous. So if we see a polynomial graph, it's something that is going to continue throughout the entire domain. There's no breaks in it. Okay, a non-example would be something, this is kind of a rough graph here, but something like a piecewise function would not be a polynomial graph because we see this break in here, right there, it's not continuous. Secondly, it is something that is smooth, it is not jagged. So for example, our absolute value graph that we learned last chapter would not be a polynomial function because it is not smooth. Thirdly, end behavior. Okay, and this is going to be one of our key focuses today. And there's really 4 different things that we could think about. And we're going to look a lot into this. But we want to see what is happening to the y value as x is going to positive or negative infinity. And what we really care about here, and you could kind of see that it's written, is we care about the leading term. So we know our leading term, we are either going to have an even exponent or an odd exponent. So let's say we had an even exponent that had a positive coefficient. That would be something like, for example, y equals x squared. To the right, it would go to positive infinity, and to the left, it would also go to positive infinity. So that's telling me that it is increasing in both directions. If we had a negative coefficient, that would be something like y equals negative x squared, and we know that that negative makes it a reflection over the x-axis. So to the right, it would go to negative infinity, and to the left, it would also go to negative infinity. So even though this is a new concept, we've actually seen this before. We just need to think about it in a slightly different way. Okay, so often if you're getting confused, I always tend to kind of think back to a basic example. Even if it said like y equals x to the 4th, I might just think about y equals x squared because I know how that behaves. Now our other option is if we had an odd exponent. So let's say we had a positive coefficient like y equals x cubed. We know that to the right it would be going to positive infinity. However, to the left it would go to negative infinity because it is increasing across the domain. Negative coefficient would be like something like y equals negative x cubed. To the right, that would go to negative infinity, and to the left, it would go to positive infinity, because I know it is a reflection of what we had in our first graph. Okay, so these are the only 4 options we will see. We just need to know what's happening. And once again, my suggestion is if you're getting stuck, I would either just refer to a basic example like I did here with x squared and x cubed, or you could, if it's a portion where you could use your graphing calculator, you could graph it and kind of see how it's behaving. Next thing, and we talked about this a little bit last time, our maximum number of real zeros, and those are the x-intercepts, is equal to the degree. And the reason why we will not always have the exact same number as the degree, there's really 2 different reasons. Sometimes we will get a multiple of a 0 at a specific point. Secondly, sometimes we will get imaginary answers. I know you guys love imaginary numbers, but they are coming back this chapter, and even though we don't really care about them today, we will later on in this chapter. And so if we have imaginary numbers, that is going to definitely detract from my real zeros. Next, our maximum number of relative extrema is our degree minus 1. And the y-intercept is our constant. Okay, so I'm just going to scroll over here, and this is an example of a polynomial function. Just based on the end behavior here, I can tell that it is a positive even integer, or even exponent, I'm sorry, not integer. And I can see that it crosses the x-axis 4 times, so I'm thinking that this is going to be some sort of x to the 4th. And I can see that my constant goes through at -2. At this point, we're not really going to do much more, but I'm just showing you how we can see some info from here. Later on in this lecture, we're actually going to learn how to write the equation if I know that these are our 4 zeros. So today you're definitely going to have to figure out in behavior. Sometimes we call it left hand and right hand behavior. So it says find the left hand and right hand behavior of the following polynomials. So if we look at A there, let me kind of zoom in here. Just a reminder, all we care about is this leading coefficient. So some things I see, it is an even exponent, and it has a negative coefficient, and I'm going to abbreviate coefficient there for us. So what this tells me, it tells me that to the right, it is going to -infinity, and to the left, it is also going to -infinity. Okay, so that's really the only thing that we have to answer on this. We just need to know what direction things are going. So if we look at B, f of x equals 2x to the 5th plus 2x squared minus 5x plus 1, that can look super confusing, but just a reminder, all I care about is that first term. We can see here that that has an odd exponent and a positive coefficient. So that means to the right, it is going to +infinity, and to the left, it's going to -infinity. And once again, if you guys have your graphing calculators out right now, it might be a good idea just to go ahead and put these functions in your graphing calculator to get some additional practice. And it's also just going to confirm what we are saying. Now, I've said this already, but I want to stress that this test is a 2-part test. And one of the parts, you are not going to be allowed to use your graphing calculator. So it's important that we know how to do this without the graphing calculator as well. For C, f of x equals -2x to the 5th minus x squared minus 4x minus 1. I'm just looking at this leading term. And we have an odd exponent and a negative coefficient. So that means to the right, it is going to -infinity. And to the left, it is going to +infinity. This is super repetitive, but I'm hoping we're getting the hang of it. Y equals -x cubed plus 5x minus 2. Once again, I have an odd exponent and a negative coefficient. So I'm going to go ahead and say that to the right, it is going to -infinity. And to the left, it is going to +infinity. So I just want to show us for a moment, for C and D, even though these functions will look very different from one another, their end behavior is the same because our leading term has the same type of exponent, even or odd, and the same type of coefficient, in this case being negative. Last but not least, E, okay, I'm looking at x cubed here. And I have an odd exponent with a positive coefficient, so that means that to the right, it's going to +infinity, and to the left, it's going to -infinity. So this is something that it really is not tricky at all, but we do need to spend some time memorizing what's happening. So the next thing we're looking at here is more explanation of relative extrema, which we know is the term for a relative min or a relative max. So if we look at A, first of all, I can see that our degree here is 4, which tells me that the maximum number of relative extrema is going to be 3. I'm going to go ahead and look at B on this paper, and then I'm going to go into my graphing calculator to actually demonstrate how we would find these, which we should actually know really, really well because we've spent a bunch of time on our graphing calculator. So if we look at this second one, I just want to point out here This time, I'm thinking that I could have up to 4 relative extrema because our highest exponent is 5, and we know 5 minus 1 is 4. So right now, get out your graphing calculators and let's see how accurate this is to what we actually see. Okay, so I went ahead and pressed y equals on my graphing calculator, and I'm going to go ahead and type in x to the 5th power plus 3x cubed minus x plus 6. So I'm going to go ahead and graph this, going zoom 6. And I'm waiting patiently for it to graph here. And if I look at this, oh, and for some reason I did B first. I don't know why. But what I want to show us is it's kind of unclear if we have some relative extrema here or not. So I'm actually going to zoom in. I'm going to go up top here. Okay, because I think this right here is the region where some of those relative extrema might be. So I'm going to zoom in around to there. And it appears like we might have a max and we might have a min there. So I'm going to go ahead and go back to zoom 6 just so I can see more of my picture. And I'm going to choose second calculate, and I'm going to try and see if there's a max value. So if there was a max value, it would be right over here. So I'm going to go to the left a little bit and press enter, and then go to the right and press enter, and then put in my guess. And it tells me there is a maximum value there of negative 0.324, comma, 6.218. And then I'm going to go ahead and repeat the process for what looks like it could be a minimum value. So I'm going to scroll to the right and press enter, and then scroll to the right even further and press enter and put in my guess. And it tells me that there is a minimum at 0.324, comma, 5.782. So to me, those look like the only mins and maxes. It looks like it's continuing down and it's continuing up. If I really wanted to double check that, I could zoom out. And I'm going to go back to like having 0, 0 be the center of my graph here. So I'm using those arrows to go ahead and control those. Okay, that's close enough for me. So I'm waiting for it to graph. And this really shows me it doesn't look like it's going to cross the x-axis again. And some things we should know, since it was x to the 5th and it was odd and positive, it should go down to the left and up to the right. That would make sense based on end behavior. Okay, so I'm going to clear that out now, and we're going to go ahead and look back at that first function a, which was 2x to the 4th, which before I do anything else, that tells me it should be going up in both directions, minus 6x squared plus 1. And as we saw in part B, even though we said that there's a maximum of 4 relative extrema, we only saw 2. Here, I'm thinking that there could be up to 3, so I'm going to go ahead and graph this. So zoom 6, and I'm waiting patiently. There we go. And to me, it definitely looks like we have 2 minimum values and 1 maximum value. So once again, I'm going to go second calculate minimum, and I'm going to scroll over to the left and press enter. I'm going through this pretty quickly because we've practiced this quite a bit so far. So my first minimum is negative 1.225, comma, negative 3.5. Now I'm going to go ahead and find that max value. So I'm to the left, I'm going to keep scrolling, I'm to the right, and I'm going to put in my guess. Going to put in my guess. There we go. And we get this weird value, and you may not have gotten that, but remember this is scientific notation, so this is really telling me 0, 1. And then I notice I have one more value that is a minimum, so I'm going to press enter because I'm to the left. I'm going to scroll to the right and press enter, and then put in my guess, and I get 1.225 comma negative 3.5. So once again, the way we find mins and maxes is almost identical to what we did last lecture with our quadratic functions. Okay, so now we're going to be finding the zeros of polynomial and graphing them without using a graphing calculator. So there are 5 different things we're going to be doing here. First of all, we're going to find all of the zeros. Secondly, we're listing the x-intercepts, which are all of the real zeros. And the key thing here is an even number of duplicate zeros will be a bounce on the graph. And we will see an example of what that looks like. We're going to find the y-intercept. We are going to determine the end behavior, and then we are going to go ahead and sketch the graph. Okay, so we're starting off with one that looks like what we did last section, and I'm going to begin by actually going through and finding all the zeros here. So I'm going to go ahead and set this equal to 0. So I have 0 equals 5x squared minus 5x minus 5. And, oh, I'm sorry. It is, there we go, minus 10x minus 5. And I notice that we have a 5 in everything. So since we have an equation, I can divide both sides by 5. And I get 0 equals x squared minus 2x minus 1. And at this point, it's really open-ended. I always look to see if I can factor first, but in this case, I don't know of any factors of negative 1 that add up to be negative 2. So I know that this is not factorable. So we're going to have to go ahead and solve it using either the quadratic formula or completing the square. I actually would prefer completing the square in a problem like this, but remember, whatever you do is fine. So I'm going to take x squared minus 2x, and I'm going to bump the 1 over. And I don't know why I'm writing that out. I know I'm going to take that middle coefficient, which is negative 2, and divide it by 2 and square it. So I'm adding 1 to both sides. So this becomes x minus 1 squared equals 2. When I square root both sides, I'm going to put my plus or minus, and I get x minus 1 equals plus or minus radical 2. So x is equal to 1 plus or minus radical 2. So that is the first characteristic of this graph. So I'm just going to go ahead and say plus or minus 1. Oops, I don't know why I wrote plus or minus in front. That goes after. Okay, there we go. 1 plus or minus radical 2, 0. The second thing they asked us to do was list all of the x-intercepts. And that is all the real zeros. Now, these are real. There we go. Somehow, I'm like out of control here. I wanted to be on a laser. There we go. Okay. These are real even though it has plus or minus a radical because I don't have imaginary numbers. So what I'm actually going to do is I know that I can't graph that off the top of my head. So I'm just going to write that is approximately 2.40 and negative 0.40. Okay, and I know normally we give answers that are much more exact than this. However, I don't know about you guys, but I'm never super accurate on my graphing. So this is kind of a better way for me to write it because I can approximate to the nearest tenth on my graphs, and that's great. Okay, third thing asked me to find the y-intercept, and we've previously learned that that is the constant. So our y-intercept is 0, negative 5. Then we have our end behavior. Okay, so we need to determine what is happening to the right and what is happening to the left. We know that it's all dependent upon, and let me scroll all the way up here, this leading term. So since this leading term is positive and it has an even exponent, that means that it is going up to positive infinity in both directions. Okay, so those are the 4 things that we're going to have to go ahead and list. Now, if I'm graphing this, okay, notice that we have 3 different ordered pairs in this case. And if we wanted to be even more exact, we could find all the mins and maxes as well. And today we're not. I think we have enough stuff going on here. So know that when we graph this, it really is a sketch. So I'm going to plot 2.40 and negative 0.40, and I'm also going to plot 0, negative 5. I know it's going up in both directions, so it needs to be going up in both directions, and I'm going to make it so it goes through those ordered pairs. Now you guys could have graphed this differently with a minimum value being somewhere over here or down there. Anywhere between these 2 points we could have a minimum, and we're not doing enough work to find exactly where that's at, even though we're capable of it. This is all I would be looking for. Okay, so number 2. This one looks a little frightening because it is x to the 4th minus 5x squared plus 4. But whenever I see this trinomial, that's x to the 4th x squared constant, I'm thinking in my head that I can factor that. So I'm actually going to say 0 equals x to the 4th minus 5x squared plus 4. And I need to think what factors of 4 add up to be negative 5. And in this case, okay, I know it's going to be x squared and x squared. I know it could be x squared minus 4, x squared minus 1. I can actually factor these further to be x plus 2, x minus 2, and I'm running out of room, so I'm just going to write it below like this. X plus 1, x minus 1. So when I set all of those equal to 0, I get x equals negative 2, x equals 2, x equals negative 1, x equals 1. And if we look back at our function, having 4 zeros makes sense because our degree here is 4. So let me scroll out a little bit. The first thing I'm going to do is I'm going to write negative plus or minus 2, 0, plus or minus 1, 0. And we could write them out separately, and that's fine. I know that my real zeros are the exact same values. Our constant this time is 4, so I have an ordered pair of 0, 4. And our final thing we need to do is our in behavior. So if I look at x to the 4th, I see that it's an even exponent and it's positive. So to the right, it's going to positive infinity, and to the left, it's also going to positive infinity. So when I'm sketching this graph, and yes, sketch is the key word here, it's not going to be as accurate as if we were graphing with our graphing calculator. I have points at 2, 0, 1, 0, negative 1, 0, negative 2, 0, and 0, 4. And I know it's going up to the right and up to the left. So I'm going to go ahead and kind of draw something that looks like a W shape. And once again, if you drew your minimums to go down further, that's fine. Okay, the key thing is I need to see this information that we wrote down on our actual graph. Number 3, this time, it looks like we might have 5 zeros. And I actually don't know any way to solve this other than factoring at this point in time. We will learn some alternate methods later on in this chapter. So I'm going to go ahead and say x to the 5th minus 6x cubed plus 9x equals 0. Even when we learn our alternate methods, factoring is often the quickest way still, if it's applicable. I notice I have a GCF of x, so I'm going to factor out an x, and I'm left with x to the 4th minus 6x squared plus 9, and that should look really, really familiar to us because it's the same type of pattern as we saw in that last problem. So I need to think what factors of 9 add up to be negative 6. And I'm thinking it's going to have to be -3 and -3. So when I set these all equal to 0, I get x equals 0. X squared minus 3 equals 0, so x squared equals 3. And x equals plus or minus radical 3. And then I also have x squared minus 3 equals 0, so I get x equals plus or minus radical 3 again. And this time, I have some weird things going on here. I notice that I have what we call double zeros. That means I get the same answer 2 different times. And what that signifies to me on my graph is that we are going to have some sort of what we call bounce. So it's going to bounce off of the x-axis. So let's go ahead and just kind of list these ordered pairs here. So I'm going to say 0, 0, plus or minus radical 3, 0, and then plus or minus radical 3, 0. And honestly, if you wrote it without writing those values twice, I would give you full credit. But I just think it's helpful to write those down to signify to us that we do have a double zero, because it helps us know what to do. All 5 of those, yes, once again, we have 5 and our degree was 5. They are all real zeros, so I'm going to write those down. I notice when I look back at my equation that I don't have a constant value, so that means the constant is 0. So we actually have an ordered pair of 0, 0. And I already could see from 1 and 2 that 0, 0 was the solution. Okay, and then lastly, we need to know what's happening to the right and what's happening to the left. So if we look at x to the 5th, it is odd and positive. So that means to the right, it is going to positive infinity, and to the left, it's going to negative infinity. And if we had wanted to, for number 2 here, I could have written those as decimal values. Like that would be great also. Okay, I would accept either answer there when we're writing down what those actually are. So in my calculator right now, I'm actually going to figure out, okay, what is the square root of 3? And it is like 1.7. So I'm going to go ahead and graph 0, 0. And then I have like 1.7, 0, and negative 1.70. I know it's going down to the left and up to the right. So what's going to happen here, since we have a double zero both here and here, we are going to get what we called a bounce. So when I'm graphing this, I know it's starting down below, it's bouncing and then going through, bouncing again, and then continuing up. Okay, so key thing here is this idea that when I get the same answer twice, notice it's not crossing through the x-axis, it is bouncing off of it. It's not crossing through the x-axis, it's bouncing off of it. And let's say I forgot about the bounce, I would tend to have some issues, because if I had crossed through here, there's no way I could get to what we said the y-intercept. If I had crossed through here, it would be decreasing, going down to negative infinity to the right, and we said it should be going to positive infinity. Okay, so the final thing of this lecture, we are going to find a polynomial given the zero. So this is really kind of the opposite thing that we're doing. Okay, so if f is a polynomial function and a is a real number, the following statements are equivalent. X equals a is a zero of the function f. That means that x equals a is the solution of this function because our output would be 0. X minus a is a factor of the polynomial, and a comma 0 is an x-intercept of the graph of f. And that's really stuff that we've talked about, but the key thing I want to point out here is number 3. X minus a is a factor. Okay, so the directions here tell us to find a polynomial with the given zeros. And I want to point out there are many correct answers because multiples of the same equation will work. I personally like writing it in the simplest form because that's the least amount of work for me to do. So the method we're going to use, based on the given zeros, we are going to write out the factors of the polynomial, then multiply and simplify. So it really is like we're going backwards instead of seeing what the function is and finding the zeros. This time we know the zeros and we're going to try and find that particular function. Okay, so for number 1 here, I'm going to start by writing f of x, or if you wrote g of x or whatever, that's fine. But we know it's an equation, so it has to be y equals f of x equals something of that nature. They're telling us that our two zeros are 0 and 3. So with a 0 of 0, my factor would be x minus 0. With a 0 of 3, my factor is going to be x minus 3. So notice the factors are always x minus the 0. So that would be kind of the first thing that I'm looking for, and in fact we call this factored form. And if you had just written this as x, I'd be totally fine with that. Now though, we do need to simplify it, so I'm going to write f of x equals x times the quantity x minus 3, and I'm going to multiply that by distributing this x to both terms, and I get f of x equals x squared minus 3x. Okay, I cannot simplify this any further. So we call that our simplified form. So our math today isn't going to be that difficult. It just might seem that it's slightly time consuming. So let's go ahead and look at number 2. So I'm going to say f of x equals x minus negative 6, which we know would be plus 6, and x minus 2. So that would be the factored form. Now if I wanted to go ahead and simplify this, we know we need to FOIL. X times x is x squared. X times negative 2 is negative 2x. 6 times x is 6x. And 6 times negative 2 is negative 12. We can combine some like terms here. So I get f of x equals x squared plus 4x minus 12. And here's the thing. Obviously, we could factor this because we know that's where those two numbers come from. Our goal here is to write an equation in simplified form. So this would be our final answer. Number 3, one thing I haven't mentioned. On 1 and 2, it makes sense that our answers here were x squared, that they were quadratic functions, because we had 2 zeros. There we go. In both of those particular problems. Number 3, I have 3 zeros, so I am thinking that my answer is most likely going to be x cubed. And it's not most likely, it is. So I'm going to write x minus 0, or if you just wrote x, that's fine, but I just am trying to be consistent here, times x minus 2 times x minus 5. So that's our factored form. When I'm simplifying this, I have x times x minus 2 times x minus 5. Now, I always tend to FOIL first and then distribute the x after that. So x times x, I get x squared. X times negative 5 is negative 5x. Negative 2 times x is negative 2x. Negative 2 times negative 5 is 10. So I would get f of x equals x times x squared minus 7x plus 10. So my final step here, I need to go ahead and distribute this x to all 3 of those terms. So I get x cubed minus 7x squared plus 10x. Okay, so one thing for us, and one way that we can double check our answers here if we're allowed to use our graphing calculator, if you went ahead and graphed this function on your graphing calculator, you should notice these 3 answers being the x-intercepts. Also notice we do have x cubed and I have 3 zeros. If that didn't match up, then you know that you made a mistake somewhere. Last but not least here is number 4. And number 4, even though we only have 2 zeros, I'm going to put a star by it because I think it looks like it is the most difficult. So let's go ahead and get started. So I'm going to say f of x equals, and this time I know it's going to be x minus 1 plus radical 3, and I'm putting 1 plus radical 3 in parentheses, times x minus 1 minus radical 3. So that would be the factored form of this problem. Now, technically, this would be like x minus 1 minus radical 3 times x minus 1 plus radical 3. And I'm getting that from distributing those negatives. Now, we know when we are multiplying a trinomial by a trinomial, I'm going to distribute one term at a time. So I'm going to start here with the x. So x times x is x squared. X times negative 1 is negative x. X times radical 3, I'm going to write it as radical 3x. So now we're moving on to this negative 1. Negative 1 times x is negative x. Negative 1 times negative 1 is positive 1. Negative 1 times radical 3 is negative radical 3. Last but not least, negative radical 3 times x, I'm sliding over here, is negative radical 3x. Negative radical 3 times 1 is positive radical 3, and negative radical 3 times positive radical 3 is minus 3. And let's be honest, this looks like a giant mess. And yes, this is going to be even more fun when we do it later in the chapter and we have imaginary answers as well. But the good news is we know in most equations, we don't see things like radicals or imaginary values or things like that in the actual equation. So those terms should cancel out. In fact, when I go to add all my like terms together, I get f of x equals x squared. Okay, and I notice I have negative x, positive radical 3x, negative radical 3x. These radical 3x's cancel each other out, and I'm left with minus 2x. Then I need to go ahead and add my constants together, and I notice I have a 1 and I have a negative 3, and I have a negative radical 3 and a positive radical 3. Once again, these radical 3's cancel each other out, so I have 1 minus 3, which is negative 2. So our answer is f of x equals x squared minus 2x minus 2. So if you go ahead and graph that function, or even if you tried to work backwards and solve it, you would notice that these would be the two zeros. So once again, hopefully this gives you guys a good overview of what we can do with some of our higher order polynomials, and throughout this chapter we will continue to build on this knowledge.